Okay, we have our good old particle problem with velocities and acceleration and speed increasing, decreasing, but this is a pretty good problem for us. I think we can handle doing this really, really well. But just take note of a couple things there. We got particle P, and this is the position function. Particle Q, that's the velocity function. It also gives us the initial position of particle Q. So part A says find the velocity of particle P. So if this is the position function, we know the order goes position, velocity, acceleration, which means we need to take the first derivative of that position function. So just that's a constant which will carry down. The derivative e to a power is e to a power times it by the derivative of that power. And you get this 4e to the negative t, part A done. That's your velocity. It's just your first derivative. Make sure that this whole problem reminder is without a calculator. All right, part B says find the acceleration of particle Q and then do something else. Let's just focus on the acceleration part. This is the velocity. We know to get from velocity to acceleration, we just take the derivative. So make it a power, multiply by the power, decrease the power by 1, boom, there's the acceleration. That's the first part of part B. And then it turns right around and asks us, when is the speed of the particle Q, when is that decreasing? All right, find all the times when the speed of the particle is decreasing. So reminder, and this is in your blue packet right here. Speed is increasing if the velocity and acceleration have the same sign. Speed is decreasing if velocity and acceleration have opposite signs. So it's saying find the times where the speed is decreasing. So I jotted down for myself, this is part of my justification here. They like to see this. Speed is decreasing when velocity and acceleration have opposite signs. Now, they gave us the velocity, okay? And notice that that's squared. I have a positive number up top, a squared on the bottom. That velocity is always positive. So if the velocity is always positive, what we're looking for the speed has to be decreasing is where the acceleration is going to be negative then, because we want these to have opposite signs. So velocity is always positive. Let's check out when the acceleration is negative. That's where the speed is going to be decreasing. So that's why I kind of just jotted that down, talking myself into getting this answer right here. This is the acceleration that we just found. I want to figure out when that's negative, when that's less than 0. Now, if you notice, the -2, that's negative up top. So I'm looking for where this t cubed then is going to be positive, because then I'll have a negative number over a positive number. That'll give me a negative fraction right there. So I just said, hey, where's t cubed greater than 0? That's when t is positive. T is negative and you cube it, you get a negative number. If t is positive and you cube it, you get a positive number. And so t is greater than 0. So when t is greater than 0, that acceleration is negative and the velocity is always positive right there. So I just kind of stress that, but that's what we're looking for. When is the velocity and acceleration have opposite signs? That's when the speed is going to be decreasing. That's when t is greater than 0. Okay, moving on to letter C. It says find y, the position of particle Q. So notice that it gave us the velocity function for Q, and we want to find the position function. Now, anytime you need to find a position function, you always got to take into account the initial position, because that's why they give us this here. So sometimes when I first read that problem, you might even underline that at the beginning. So at t = 1, the position we're at is at 2. So at t = 1, we're at 2. That's where we're at. And if I know where I'm at t = 1, then I'm going to pick it up right where I left off. So at t = 1, we're at 2. Let's pick it up right at 1. And then it says at time t, not at 4 or 5 to go from 1 to 4 or 1 to 5. It says at time t. So you're just going to go from 1 to some other time period in the future right there. So the initial position, and then that's at t = 1, pick it up where you left off, go to t. And we know to integrate the velocity, because when we integrate the velocity, that's going to give us the position function. But please don't just do the integral velocity. That will get you some credit to if you're telling them that I know, hey, the integral velocity is position, but always take into account that initial position. Okay, now when you integrate this is no calculator. So I got 2 plus the integral. My velocity is 1. At first I put 1 over t squared. Remember, we're not supposed to have those letters be the same. If you got a t there, just make these x's right here. And then that's all. Yeah, it's just make them x's. All right, so just integrate this. That's a very simple integral, easy power rule. And then integrate it, you get this -1 over x. Plug in, you have a definite integral between 1 and t. Plug in top minus the bottom. So this 2 wasn't there initially. I got -1 over t minus a -1 over 1, so it's +1. And then this 2 right here carries down, so I got 2 plus 1 to get the 3 minus 1 over t right there. So integrate it, take into account that initial position. Very easy integral. We can knock that stuff out. All right, letter D is actually a really nice part of the problem. It's not like a crazy part of the problem like it is sometimes there. It says as t approach infinity, which particle will eventually be farther from the origin? Now, what we need to look at here as t approaches infinity, it says you're talking about position. You want to talk about limit as t approaches infinity of this position function, and also the limit as t approaches infinity of this position function. So I have my two position functions for p and q, and let's just do the limit as t approaches infinity. So as I do limit as t approaches infinity of this guy, I got rid of that negative exponent. And when you plug in e to the infinity, that's 4 over infinity, which is 0. So that limit answer is going to be 6 for particle p. That's how far we are from the origin there. And then here, limit as t approaches infinity of the q function, the q particle, that's just 1 over infinity, which is 0. So you get 3 for that. So that's the position of particle p. That's position of particle q. 6 is bigger than 3. So guess what? That means particle p is going to be further from the origin. Peanut butter M&Ms. It's a smooth flavor there for a nice little dessert treat.